Okay, this second video, we're just gonna focus on an example and then talk about the extreme value theorem. Okay, so the first example is sketch the graph of a function f that is continuous. It gives you the interval on the interval 1 to 5 and has the given properties. Okay, you have a couple like these in your homework. And then after this example, there's if you have my lecture notes, it says have them try. You should go ahead and try the problem after I go through this one. Pause the video. I do have the solutions up on Blackboard for all the problems that I have you guys try. So give them a try, see how you do, and then look at my solutions to compare your answers to my answers. Okay. So let's see. We have an absolute max at 5, absolute min at 2, local max at 3, local min at 2, and 4. Okay, so we're working on the interval 1 to 5. Now all we have to do is draw a function that satisfies these 5 properties, okay? Now it doesn't have to be anything special, it doesn't have to be perfect. All you have to do is satisfy these 5 properties, and once you do that, you're done, okay? So I'm going to go ahead and erase this. I'm going to draw just any old y-axis. You don't even have to label the y-axis. But now here's my x-axis, and we're at 1. Here's 2, 3, 4, 5. Okay, so we only have to draw our function between 1 and 5 because that's all it's asking for. So let's see, our first thing, it says absolute max at 5. So somewhere here at 5, this has to be the highest point on the graph. I'm going to put a dot there. Now anytime I make a maximum, or make the graph go up, I cannot make it higher than that point because it's supposed to be the absolute max. Now, the next thing says absolute minimum at 2. So when we're at 2, we have to be at the very bottom of the graph. I'm just going to put a dot way down there. So no other point on this graph should go lower than this dot at 2. Let's see, local max at 3. Okay, so somewhere here at 3, I am going to have a maximum. So we know we're going to go something like that. It's going to go up somewhere like that. You know, this is going to go down. This is going to go down. Well, I'm only doing that maximum, minimum. This right here is the absolute maximum, but I'm not going to draw anything like that. All I know is it goes up because I don't know anything past 5. I don't know what it does past 5. So let's see. Local max at 3. Local min at 2. So since this was an absolute minimum, this is also a local minimum. So we don't have to redraw that. It's already there. And another local minimum at 4. I'm going to put it right there. Okay, so now I know that this graph starts at 1. Now I can make it start anywhere at 1. Doesn't matter where. Let's make it start right there. You can make it start down here. It doesn't matter. We just have to draw a graph that satisfies all the conditions. So now I'm going to go down here. It's going to go something like that. There we go. So we could see we have our local min here. We have our local min here. We have our local... Sorry, I wrote min right there. That should be a max. Should definitely not be a minimum. Here we have a local min. And we also have our absolute min. And then our absolute max, since our graph starts here, and our graph ends there. This is the highest point on the graph. Here's our absolute max. So we satisfied every single condition that it was giving us, okay? So here's what the function could possibly look like, okay? Alright, so you should take a moment, pause the video, go ahead and try sketching that one in my lecture notes that I tell you guys to try. Again, compare it with my answer that you can get on Blackboard. Now, we're going to talk about something important. It's called the Extreme Value Theorem. Again, I'm not going to write it up on the board. You have the notes in front of you. I'm going to read it, and then we're going to draw a picture. Okay? The Extreme Value Theorem says if f is continuous on a closed interval from a to b, then f attains an absolute minimum or maximum value, f of c, and an absolute minimum value, f of d, for some numbers c and d inside of our interval a to b. So what the Extreme Value Theorem is saying is that it guarantees us that there is a maximum value or a minimum value if the conditions are satisfied. The conditions being that, for one, the interval has to be closed, meaning it starts at some point and it ends at some point. If you recall in the last video when we were talking about x squared, how it had no absolute maximum, that's because it kept going, okay? Whereas our other example where it was like y is equal to 3x to the fourth, so on, so on, so on, we started at one point and we ended at another point, okay? So that's a closed interval. We definite start, definite stop. So now if our function is continuous on that interval, those are our conditions. If those two conditions are met, then we know for a fact that f has a maximum value and f has a minimum value inside that interval. Now, let's go ahead and draw a picture and see what this would look like. This, again, is some generic graph. We're going to start at A. We're going to end at B. A is going to start, let A start down there. Let B end up here. And if A starts down there, the graph could do something like that. I don't know, I just drew a random graph, okay? Now, let's see if the two conditions are met for the Extreme Value Theorem. The Extreme Value Theorem says if our function f, whatever f is, this is f, is continuous on the closed interval. Closed, I've got a filled-in hole at the start. I've got a filled-in hole at the end. My interval here is definitely closed. It goes from A to B. And it's continuous. Everywhere I drew, I did not lift my marker up off the board. So this is a continuous function on this closed interval. The Extreme Value Theorem guarantees that there is an absolute minimum and there is an absolute maximum value on this graph. Now, you could try this for any kind of graphs you want to draw. It is a true statement. If I look here, that right there would be the absolute maximum. Everywhere on this function, nowhere is higher than this point right here if I were to look at the y values. Now we also have down here the absolute minimum. No other point is lower than this point right here. And again, you start at A, start at B, draw a different graph, and you're going to see that you're definitely going to have an absolute maximum and definitely going to have an absolute minimum somewhere on this graph. Now, here's in my opinion, a really lame example. f of x equals some number, just say like 5. That's a really bad 5. Let me redo that. Let's just say we're talking about the interval 1 to 6. Well, from 1 to 6, this just looks like a horizontal line. It still satisfies the conditions of the extreme value theorem. It's continuous on the closed interval from 1 to 6. In this case, the absolute maximum is 5 and the absolute minimum is 5, and it occurs everywhere. Okay, there's just strange examples, really simple examples, okay? But it still worked. Extreme value theorem worked. Usually we're more interested in different examples, ones with more hills and valleys in it, okay?